Welcome back, everyone. Get ready, because today we're diving deep into something that might sound a bit intimidating at first: random features in machine learning. But stick with us. Trust me, it's way cooler and easier to grasp than you might think.
It really is.
Okay, so to start us off, can you give us a quick overview of what these random features are all about?
Sure. The basic idea is that we can use random features as like clever shortcuts.
The shortcuts.
Yeah, to make some complex machine learning methods much faster without, sacrificing too much accuracy.
So it's kind of like finding a shortcut through a dense forest, but still enjoying the beautiful scenery along the way.
Exactly, a perfect analogy. And, you've given us some fascinating research to dig into today on a specific type of random feature. It's called the uniformly rotated Mondrian kernel.
Okay, wow, that name definitely sounds a bit like something out of science fiction. But the paper explains that this method is inspired by, well, something called the Mondrian process.
Right.
Can you break that down for us?
Yeah. The Mondrian process uses random partitions of data, almost like, dividing a cake into random slices.
Okay, I'm starting to get the picture.
And this uniformly rotated version, well, it takes those slices and then, get this, it randomly rotates them.
So we're slicing and dicing data and then giving it a good spin. I am intrigued. But before we get too deep into this whole rotation idea, the paper mentions something about the Laplace kernel.
Right.
It says it's being approximated by both the standard Mondrian process and something called random bitting features. Can you help us understand what kernels are in this context and why approximating this Laplace one seems to be so important?
Absolutely. So kernels in this context are essentially functions. They measure the similarity between data points.
Similarity, huh?
Yeah. Think of it like judging how close two friends are based on their shared interests. The more interests they have in common, the more similar they are.
Okay, that makes sense. So what's so special about this Laplace kernel? What kind of friendship does it excel at measuring?
Well, the Laplace kernel, it's particularly good at capturing similarity when the data is stretched out, kind of in specific directions. It's like, think of those friends who might not have a ton in common overall, but they share one very specific niche hobby.
Oh, I see.
And that creates a strong bond between them. The Laplace kernel can pick up on those kinds of relationships in data.
Interesting. So it's like finding those hidden connections that might not be obvious at first glance. Okay, so to now back to this whole rotating thing. Why bother spinning those Mondrian slices? What's the advantage of that?
So the regular Mondrian process, it can sometimes be biased, towards certain features, particularly those aligned with the axes along which it makes its cuts.
Oh,
yeah, like the slices. And this can limit its ability to see similarities in, more complex data patterns.
So it's like judging our friend group based solely on their love of, say, vintage video games?
Exactly.
We might miss out on other shared interests that connect them in different ways.
100%. Rotating the Mondrian process, it forces it to consider similarities, from all possible angles. And this leads to a more flexible and balanced approach, giving us a much richer understanding of the data.
Okay, that makes sense.
And importantly, it makes the resulting kernel what we call isotropic.
Isotropic, does that mean it's like somehow more fair in how it judges similarity?
Precisely. An isotropic kernel, it treats all directions equally. So, it avoids biases towards specific features. Think of it like judging a book. You'd want to judge it by its overall content and style rather than just focusing on its genre or, say, the author's background.
Now, that's a judgment I can get behind. And you know what else really impressed me about this paper? The researchers actually proved mathematically how quickly this rotated Mondrian method converges to its, ideal performance.
Right.
They even provided a visualization of the resulting kernel.
Yeah.
That's pretty cool.
Yeah, it is. That mathematical proof gives us, confidence in the method's reliability. And the visualization, which you can find in Figure 3 of the paper, it helps us picture how this kind of abstract concept translates into a concrete shape.
Okay, I'm definitely going to check out that visualization. But before we get too lost in the math here, can you explain why this convergence speed is so important in practical terms? I mean, what does it actually mean for using this method in the real world?
Sure. It means that, we can be confident that the method will find a good solution quickly, even when we're dealing with, large and complex data sets.
Right.
And this efficiency, it's crucial for real-world applications, where time is often a limiting factor.
So it's like having a fast track to insight without sacrificing accuracy.
Exactly.
I like the sound of that.
And that's, one of the key benefits of random features in general. They offer like a clever way to balance speed and accuracy. And that opens up new possibilities for machine learning, well, in a wide range of fields.
Okay, so we've covered a lot of ground in this first part of our deep dive. We've learned about random features, the Mondrian process, kernels, and even a bit of math. But before we move on, I want to make sure we're all on the same page.
Sure.
Can you give us a quick recap of the key takeaways so far?
Of course. We started by discussing random features, as shortcuts for making complex machine learning methods faster. Then we explored a specific type called the uniformly rotated Mondrian kernel. Yeah. It's inspired by the Mondrian process of, randomly partitioning data.
Right.
We learned that this rotation helps to create a more balanced and fair approach to measuring similarity. And that's reflected in the isotropic nature of the resulting kernel. Uh-huh. And finally, we touched on the importance of the mathematical proof and visualization provided in the research paper. These, they give us confidence in the method's reliability and efficiency.
I'm with you. So building on that foundation, let's shift our focus now to the practical side of things.
Sounds good. I'm ready. And, as we delve deeper into this research, it's amazing to see how these mathematical concepts they can actually connect to real-world scenarios.
Absolutely.
Yeah.
We've talked about kernels, like measuring similarity, like judging friendships. Yeah. But how does this all, translate into something more tangible? Can you give us, a real-world example of how this uniformly rotated Mondrian kernel could actually be applied?
Okay, sure. Let's say you're a doctor. You're trying to analyze a medical image to, detect a specific condition.
Okay.
Using traditional methods, this analysis could take hours or even days. But with, these random features, especially the uniformly rotated Mondrian kernel, we might be able to speed up that process significantly while still maintaining a high level of accuracy.
Wow. So we're potentially talking about faster diagnoses, more efficient treatment plans, and ultimately better outcomes for patients. That's incredible.
Exactly. That's the idea. And it's not just limited to, medicine. We could apply this to financial modeling, climate prediction, understanding social trends. Any field where we need to analyze vast amounts of complex data could benefit from these techniques.
It's like we're giving these fields a turbo boost.
Right.
Helping them make sense of information, more efficiently and effectively. Yeah. But let's not forget that fairness aspect we talked about earlier.
Right.
We don't want these turbocharged systems making biased judgments. Right.
Absolutely not. And that's where, the isotropic nature of the uniformly rotated Mondrian kernel, it becomes crucial. By ensuring that the kernel treats all directions equally, we're helping to minimize bias in the analysis. It's like making sure that, a judge considers all the evidence presented in a case, rather than favoring one side over the other.
Now, one thing that really struck me in the paper was how the researchers actually tested this method.
Yeah.
They didn't just come up with this idea and assume it would work.
Right.
They put it through rigorous testing.
Yeah, they did. They compared the uniformly rotated Mondrian kernel to other methods like the standard Mondrian kernel, random binning features, which, by the way, is another technique that uses, data partitioning for faster analysis, and even a more complex method called Fourier random features.
Wow.
And the results, they were pretty impressive.
So it's like putting this new method through a series of, challenging obstacle courses just to see how it stacks up against the competition.
Exactly. And it performed remarkably well, even on data sets that weren't, specifically designed to favor it. And this demonstrates the robustness and flexibility of this approach.
That's really reassuring. It means this method isn't just a one-trick pony. It can handle a variety of data challenges. Okay, so we've talked about the theory, the testing, the applications. But one thing I always find, helpful is to connect these concepts to something a bit more relatable, like, pop culture, like those Science is Superheroes articles. You know the ones, right?
Yeah.
That explain the physics behind superpowers and all that.
I see where you're going with this. It's all about, making these complex ideas more accessible and more engaging, for everyone.
Exactly. So let's play a little game, okay? Ready?
Sure, let's do it.
I'll name a famous movie character.
Okay.
And you tell me what we might miss out on if we only judge them based on, just one characteristic.
Mm.
Just like the standard Mondrian might, overemphasize certain features.
Yeah.
Ready?
Yeah, hit me.
Okay, first up, Katniss Everdeen. from The Hunger Games.
Oh, okay. Well, if we just focused on Katniss's archery skills, we'd miss out on so much. Her courage, her loyalty, her strategic thinking, all these qualities, well, they make her the complex and inspiring character she is.
Exactly. Okay, next up, Indiana Jones.
Okay. Well, Indy, he's often seen as, this daring adventurer, but he's also a brilliant archaeologist and a dedicated professor who, deeply cares about preserving history.
He's got brains and brawn. All right, last one. How about Sherlock Holmes?
The master of deduction. But if we only, focused on his logical reasoning, we'd miss out on his quirks, his vulnerabilities, his deep sense of justice, and, his complex relationship with Watson.
You aced the pop culture challenge. But seriously, these examples perfectly illustrate the, importance of looking beyond the surface, of considering multiple perspectives before, forming an opinion. And that's what this uniformly rotated Mondrian kernel does for, machine learning.
Yeah.
It's like our own personal Sherlock Holmes, helping us analyze data from all angles and uncover, those hidden connections.
That's a brilliant analogy. And just like, Sherlock uses his powers for good, we can use these tools to, make the world a better place.
I love that idea. But let's not get ahead of ourselves. While this research is, incredibly promising, it's still in its early stages.
That's true. It is important to acknowledge that there's still a lot of work to be done, before we see widespread adoption of these techniques.
But that's what makes it so exciting. It's like we're on the cusp of, like a new era in machine learning, where we can not only make machines smarter, but also help them make, fairer and more insightful judgments.
And as we continue to explore these possibilities, I think it's crucial to remember that it's not just about, making machines smarter. It's about making them like partners in our, quest for knowledge and understanding.
Well said. Now, before we wrap up this part of our deep dive, let's touch upon something that really stood out to me in the paper. The researchers, they included a visualization of the uniformly rotated Mondrian kernel, which you mentioned earlier.
Yes. That visualization is incredibly valuable. It helps to bridge the gap between these abstract mathematical concepts and, something we can actually see and grasp.
So it's like translating a complex equation into a beautiful piece of art.
Exactly. And in this case, the art, it takes the form of a smooth, symmetrical shape in a multidimensional space.
Okay, I'm trying to wrap my head around those multiple dimensions. But what do the contours of this shape actually tell us? What insights can we glean from, this visual representation?
Those contours, they represent the kernel's sensitivity to, different combinations of features. The closer the contours are, well, the more similar the corresponding data points are considered to be.
So it's like a topographical map of data similarity.
That's a great way to think about it. The peaks and valleys of the contours, they represent areas of, high and low similarity, respectively.
Fascinating. It's amazing to think that we can visualize such, complex mathematical concepts in a way that, makes them more intuitive and understandable.
Oh.
It's amazing how a single visualization can, unlock so much understanding,
It really is. Visualizations, they're powerful tools for making sense of complex data.
And speaking of making sense of things, I've been thinking about something you mentioned earlier. You said that this uniformly rotated Mondrian kernel, it could potentially lead to, breakthroughs in fields like medical diagnosis and financial modeling.
Absolutely. There's huge potential there. Imagine a world where, machines can analyze medical images with incredible speed and accuracy, identifying subtle patterns that might be missed by, the human eye.
It's like having a superpowered radiologist, one who can, spot a tiny tumor hidden within, a healthy tissue.
Precisely. This could, revolutionize early detection and treatment. And it's not just, limited to medicine. Imagine algorithms that can analyze market trends with incredible precision, identifying opportunities and risks that human analysts might overlook.
So we're talking about a future where machines can help us, make better decisions, not just in our personal lives, but on a global scale.
That's the potential. But of course, with any powerful technology, there are challenges and risks to consider.
That's where the the human element comes in, right?
Yeah.
We need to ensure that these tools are developed and used, responsibly and ethically.
Exactly. We need to be like vigilant to question the, outputs of these algorithms and to ensure they align with our values and goals. It's a partnership, a collaboration between, human and machine intelligence.
So it's not about like machines replacing humans, but about humans and machines, working together to achieve something greater than either could alone.
I couldn't agree more. And as this research continues to evolve, I'm incredibly excited to see what the future holds.
Me too. It feels like we're standing at the edge of a new frontier.
Yeah.
Full of possibilities and like uncharted territory.
And who knows what incredible discoveries await us. Maybe one day, these machines will even be able to help us unlock the mysteries of consciousness itself.
Well, that's a bold prediction.
Yeah.
But after, diving deep into this research, I wouldn't bet against it. The potential here is truly mind-blowing.
It really is. And it all started with something as simple as randomly rotating some data slices.
Amazing how something seemingly like small can spark such, profound possibilities.
That's the beauty of, scientific discovery. You never know where a single idea might lead.
Well, on that note, I think it's time to wrap up this deep dive. We've explored the intricacies of random features, unlocked the secrets of the uniformly rotated Mondrian kernel, and even, ventured into the philosophical implications of this research. It's been an incredible journey.
I couldn't agree more. It's been a pleasure sharing this adventure with you and our listeners.
And to all our listeners out there, thank you for joining us on this deep dive into the world of random features. We hope you've enjoyed the journey and, come away with a deeper understanding of this fascinating field.
And remember, the quest for knowledge, it never ends. Keep exploring, keep questioning, and keep those brains buzzing.
Until next time, happy diving.